Hi everyone, welcome back to Adrian's Digital Basement. On today's video, I'm going to be working on an Amiga 2000. This machine was donated to me from a viewer named Andy, and he told me that the machine had suffered battery leakage, which is really common for these machines, and it was no longer working. He had taken the machine apart and decided after looking at it that it was beyond his ability to fix, so he donated the machine to me. Now I started working on the machine and I didn't think I was going to make a video because there's already a ton of really good videos out there on fixing Amiga 2000s that have had battery leakage. But as I started working on this machine, I found that there was maybe some stuff that would make an interesting video because I was trying some new techniques on the corrosion and then I had to do a bunch of troubleshooting and fixing to get the computer working. So where this video begins, I'm already partway through the cleaning process when I realized I probably should make a video on repairing this computer. So anyways, let's get right to it. So on the Amiga 2000 motherboard, the battery, which is right here, very commonly leaks if it's old and discharged for a long time. It's a nickel cadmium. And of course it leaks its gunk all over the motherboard in this area. Here's the CPU socket. This is the ROM and keyboard port here along with the mouse port. And then this slot here, which you see this purple stuff on it, this is the accelerator slot for the CPU upgrade. A telltale sign of leakage is that you see this green crustiness all over the socket. Now you're not seeing it on this one because I've actually already dealt with the problem. I soaked this area of the motherboard in vinegar, and what I do is because I don't want to soak the entire motherboard in vinegar, is I lay paper towel strips over the parts that have been exposed to the electrolyte, like on the ROM socket here and of course the CPU socket, and I pour vinegar on it and I let it sit there for quite a few hours. And it has the effect of getting rid of a lot of the corrosion. Now when you take a close look at the CPU socket though, you'll notice that there's some permanent damage on this socket, and there's no way this computer is going to work anymore without, at the minimum, replacing this socket. Notice that the dual wipe contacts on the CPU socket, a bunch of them are broken now, so if I stuck a CPU into there, even a good CPU, it just wouldn't make good contact. And you're probably asking, what is this purple liquid that I have poured over the CPU expansion slot? Now, just like the CPU socket and the ROM socket and some of the other stuff around here, there was a lot of this green-blue corrosion on the gold fingers that make contact with the card that you plug into this slot. And even though I put vinegar with paper towels over this for just as long as this CPU socket and the ROM socket, it didn't seem to really get rid of any of that blue-green corrosion at all. And I really wanted to clean that up before I try to get this computer working and plug an accelerator card into this slot. Now what I've gone ahead and done, and this might be the wrong thing or the right thing, I don't know, is I've poured this Naval Jelly, which I normally use to dissolve rust on iron and steel parts, onto this connector. And what's nice about this stuff is it's a really thick, viscous, pink colored gel. So when you pour this onto areas, it sticks to it and it doesn't just immediately pour off and kind of run off the edges of the board. This is what happens with vinegar, which is why I take pieces of paper towel and the paper towels kind of keep it in the appropriate areas. A couple hours ago, I poured this onto the entire slot. So now I want to wash this off and see if this had the effect of getting rid of the blue-green corrosion. Incidentally, on this motherboard, there was a lot of the blue-green corrosion on the keyboard connector and on this mouse port, but wrapping the paper towel around this with the vinegar seemed to have cleaned off the corrosion off of both of these. The board is still wet because I just washed it off in the sink, but there is no blue-green corrosion left on this connector. I don't see anything at all. Now, I'm assuming where the corrosion was, now that it's gone because of the Naval Jelly, it's probably bare copper because the plating usually gets eaten away, and that's what the corrosion comes from. So I'll probably have to make sure that I keep Deoxit on this because it creates a sort of a film, a little bit of a barrier to prevent corrosion. Now, if this were a normal trace that was exposed copper, I would just paint over that with a lacquer of some kind or a PCB paint. But you obviously can't do that on these fingers because they need to maintain their connectivity and their contact with the cards you plug in there. So I think the best thing will be for this is once it dries, Deoxit. Of course, it goes without saying the CPU socket will need to be changed as well. The ROM socket, on the other hand, seems like it's going to be fine. I am noticing in the back of the mouse port, there's still some corrosion there. So I think I'm going to turn the board up on its end like this and put some Naval Jelly right into the port there to hopefully knock that out as well. So first I want to do the smoke test. The power supply is connected. Of course, there's no CPU or accelerator, so the computer will not work. It is plugged into the video output. Let's just see what happens if I turn this on now. I assume you get some kind of a video signal. Yeah, it looks like it's synced up because, you know, I have the entire chipset installed, just no CPU. So, okay, no smoke is coming out of anything. Here is a Commodore 2630. This accelerator card was actually installed in this machine. So unfortunately, it suffered the corrosion issue as well. All that green corrosion that was on the accelerator socket. I already cleaned this up by soaking this part of the board in vinegar, and then I sort of scraped away any of the corroded solder mask and then put lacquer over it. A couple fingers had bad plating, so I've actually re-tinned those. And on the back, there's a similar story, although it's a little bit worse because there was actually a bad trace from this finger to its nearby via, so I added a bodge wire, and then I tinned these, and looks one of the fingers is partially broken off there, but it doesn't cause a problem. I've already tested this in another computer, and this board works perfectly. So let's put this accelerator in. There it is. Let's just bend the wire so it's not getting pushed on by the power supply. And now place your bets for what's going to happen. There's no CPU installed on the motherboard, but the accelerator card, which works, is in the socket. There might be bad traces. It might not work because of the CPU. There could be a lot of things, but let's just turn it on, see what happens. Here we go. I'd say we have a computer that is not booting properly. I've hooked up an LED, which I'm holding right here over the accelerator card to the motherboard. So let's see what happens. We'll be able to see if this changes brightness, which may indicate the computer is trying to boot. Here we go. There would be no change to the LED, which would indicate that this computer is not executing any code right now. Incidentally, on this computer, I haven't tested any of the other chips on here, any of the custom ICs for the Amiga chipset, so any of those could be faulty actually as well. But because I really need to be switching this socket out anyways, because I know it's bad, I might as well do that first before I do any of the other testing, because switching this out and putting the original CPU or a 68000 back in, maybe will make this computer work and I won't need to test these other chips. So for efficiency standpoint, I just should do the things I already need to do, which is change out this socket. Check out that really nice socket that I've installed there. Here's what's left of the old crusty socket. I kind of cut it up. I find it easier to get it out. Sockets are not as easy to take out as ICs, at least to me, because I can't use my hot air trick to pull the chip out cleanly without, possibly lifting a trace. So I cut it up into pieces, and then I work on the little pieces individually. Even though I had cleaned up the socket with vinegar, there was still some of the green corrosion on the underside, which may mean that the ROM socket also has corrosion underneath it. But hey, if we have a problem with this, then I can always change it later. I knew that the CPU socket definitely needed to be changed. One thing to make sure of when you have the socket off is double check that all of the traces underneath the socket have good continuity between them and the things that they go to. Because if a trace is bad underneath the socket, it's far easier to figure that out and then fix it while the socket is off than after the fact. This is the original CPU that was in this thing. Now, it had a lot of green corrosion on it as well. Now, I did sand down the legs with sandpaper, both sides. This side is just the raw sanding after I did it. But this side here, I actually tried to apply some solder onto each of the legs. Wasn't really pleased with how it turned out. I mean, I guess it's working. You don't really see the copper color while you see copper on this side. But I'm just going to call this good enough for now, at least for testing. Let's pop this CPU in, the notches down here. While I was working on the board, I also pulled out the old residual bits of the battery that were in there. It was just cut off, so the little legs were still in there. So I did that, and then I added 2 pins as well. And then I applied clear lacquer to anything that was exposed copper in this area. I know lots of people have suggested that I use PCB paint that's green color. Well, I've ordered some from China, and, due to what's going on in the world right now, it still hasn't arrived. It's been forever. So I will continue to use my clear lacquer, which, yes, is nail polish, but it's basically good enough. I've never had a problem with it. You might notice I have the oscilloscope out on the bench, and that's because I anticipate that this is not going to work, and we're going to have to do some troubleshooting. So here's an Amiga 2000 power supply. Let's plug this into the power connector here. Make sure I don't misalign it. There we go. This cable goes to my 1084 monitor, which is just over here to the left. And this is the original ROM that was in this machine, along with all the other custom ICs. I put everything back in that was original. This is 2.04 ROM. It looked a little corroded, but I cleaned up the legs on this one a bit too and stuck it back in. And that is the original socket. And here's the green LED. I just stuck it right there so we can take a look at that when I power this on. All right, and we are ready. Here we go. Where's the power switch? Here it is. Just like before, dead. Just in case anyone's wondering if this is on the right input or whatever, it is, because right now I see a faint line at the top of the screen. That's because I've shrunk the picture down and I'm seeing what's normally off the top. And this monitor always shows that at the top of an NTSC picture, kind of like a little RGB line there. I don't know what it is. Maybe it's these 1084 monitors always do that, but it's actually a good tip because now when I turn this off, that line goes away. So I know this was generating a video signal to this thing, but of course we were getting nothing. Power LED also was just solid on. So we're having exactly the same problem as before when I had the coprocessor card in there without the original CPU. So now for testing, I am armed with the 68000 pinout, and I'm gonna check the basics. We need to check the reset signal and the clock. Here's the clock signal, that looks good. It's a little over 7 megahertz, that's great. And here's the reset signal, which should stay low and then go high once the system is running. There it is, it was low to high, perfect. Next, let's check one of the address lines just to see if there is activity. Okay, so, well, no, there was a split second, and right now that indicates that the address bus is high impedance. So basically it's in a tri-state configuration right now where the processor is not trying to drive the address bus. I'm gonna pick a different random address bus. Same thing, it kind of went high for a split second and then went back to high Z. So I just checked all the data bus lines and all 16 of them are high. But on this particular motherboard, this is a version 4.4, they're all pulled high. So even if the CPU is not trying to drive them, they will be high. But the address bus on the other hand is not pulled high. So the fact that we're just seeing floating lines here indicates that nothing is driving the address bus right now. Now the next pin to look at is the halt pin. And let's take a look at this. This is active low. So when it's held low, the CPU is halted up. It went high for a second and then instantly went low. Now on the 68000, the halt pin can either be an input or an output. If the processor detects a problem, like say bus contention, it will halt itself to protect the chips on the board from shorting against each other. Or also one of the chips on the board can actually instruct the processor to halt as well, which basically just stops it from executing after it finishes what it's doing. So it's not unusual for the halt signal to go into the processor, but the fact that it's just solid low indicates that the processor is definitely not executing any code right now. And that explains why the address bus is floating and the data bus is just high with no activity, because when the processor is halted, whether it halts itself or something else halts it, it disconnects itself from the bus entirely, address and data bus. It's almost the equivalent of the processor chip just being removed from the socket entirely. Now I need to figure out if the processor is halting itself or something on the board is telling it to halt. So I'm thinking that a good way to do that is actually to just take it out of the socket, and I'm going to bend out the halt pin out of the socket so it's floating outside, and then I can actually just measure that pin versus what I see on the socket, and then that will tell me if the processor is halted itself, the pin will be low, but the input on the socket should be high. I'm definitely wary about bending pins on this CPU because the legs are so corroded already. I'm a little afraid that if I do it carelessly enough times, I might just break the entire leg right off. I have a replacement CPU, but I'd rather just keep this original one if it's working. All right, the leg is bent out. Let's power this back on. It's not gonna run, I'm sure. But it might, if something's halting the processor. No, we're still getting a black screen. So first of all, let's check the output of the processor on the halt pin. So it's low, and actually if I turn this off and turn it back on, let's see what happens. So it just stays low entirely. Now I can stick the probe past the pin into the socket, and look at that, it's high. Let's turn the power off and on. So it's low right now, and then it goes high as the computer comes out of reset, and yet the processor itself is low right now, which means it has halted itself. It is not being instructed to halt. Now, when you look in the datasheet for the processor, it halts itself when you have bus errors. You have contention errors. I'm just going to bend this chip pin back carefully. Good, it didn't break off. So right now what I need to do is go look at the schematics for the Amiga 2000 or the B2000, which is what this motherboard is, and look to see how the address and the data bus is configured on this thing. There are lots of things on the address and data bus, but I have a feeling on this motherboard, it's probably pretty buffered, meaning there are 74 LS245 transceivers between the processor and these various chips. So that means if there's something wrong with the address bus, like on one of these CIA chips, it's not going to affect the processor directly because it's on the other side of the transceiver. The same goes for the data bus. The processor is probably on its own or has a few things on its own local data bus, and then the rest of the stuff is off on the other side of transceivers. All right, sure enough, there are 6 LS245s right here that handle buffering of address and data buses. There's also LS244s over here by the RAM. There's also 2 more LS245s over here that are doing data bus buffering as well. So yes, things are quite buffered on this machine. What I found is that these Buster chip, which is this IC up here, it's the 5721, this handles all the bus arbitration between the Zorro slots and the coprocessor card and the processor. Now, all of these things can be bus masters, meaning that one of the cards in here can take full control of the address and data bus in this computer to do like DMA memory access and stuff like that. And this chip is what arbitrates all of that and allows that to happen. What that means, though, is that if this chip is having a problem, it could be instructing the buffers to do things while the processor is trying to use the bus, which would cause bus contention errors and would cause the processor to halt itself. So I think a good test is I'm just going to pull the Buster chip out of this motherboard. Looking at the schematics, this chip is what makes the Zorro 2 slots work as well as a coprocessor slot. But since I'm not using either right now for testing, let's see what happens when this is out of the computer, if it boots up or if we at least see activity on the bus or what. All right, let's see what happens. Oh, hey, look at that. We got some activity. We're getting the green death, I don't know, whatever. Let's see. Let's turn this off and on. That's like what? It's Kickstart 2.0, so that indicates what? Like a RAM error, potentially? But hey, you know what? It's actually executing code, and the LED is flashing. So that means code is actually executing on this machine right now. Excellent. Now, what I happen to have right here is the Amiga Diag ROM. This is a diagnostic Kickstart ROM for the Amiga. It replaces the regular Kickstart and offers some nice diagnostics. So let's pop this in instead of the regular Kickstart here. Make sure I have it the right way around. I don't know what happens if you plug these EPROMs in the wrong way, but it might kill them. Who knows? Okay, pop that in. Let's power this up now. Hey! That's a good sign. That's what this ROM does when you first plug it in. Diag ROM. Nice. Okay, I just had to change my frame rate because this is running in PAL right now. But there we go. 68,000, 1024K of RAM. No fast RAM, of course there's not. And this thing worked. I'm going to plug a keyboard into the front here. Let's see if I can control it. Yep, there we go. System info. Oh, this keyboard doesn't work very well. The enter key, there we go, is not good. All right, yeah, I don't know, sysinfo. I don't know, that's not particularly useful. I'm gonna run a memory check though. Let's do 2, and we're gonna do extended chip mem test, and we'll let this run through. Now, I do know for a fact that this chip mem test will test from 0 to 2 megabytes, and this computer only has 1 meg of chip RAM. So once it passes the 1 meg barrier, if we don't see any errors, what will happen is we're going to get an address error because the processor is going to try to address memory that doesn't exist. So it will crash basically, or will give us a big full screen address error. That happens on all Amiga 2000s and 500s that I've ever seen with this particular ROM. I guess it's just the way it's written. I wish I could tell it to only check up to 512K or 2 megabytes, depending on what kind of machine I'm using. So anyways, let's see what happens. We're just about to 1 megabyte here. And it's probably going to crash. But so far, no RAM errors, which is a great sign. 991K, here we go. It's about to hit 1 meg. There it is, and then it crashed. Okay, so no RAM errors, though. Excellent. So there's no problem with the memory on this machine. So it's definitely weird that we're getting that green screen with that other ROM chip. Now, this is the EPROM I burned, right? And it's working. So the socket is fine. Now, it's quite possible this chip, which is all corroded on the legs, it's just flaky. could be like trying to address like a higher part of memory or something, and then it fails. I'm going to put it back in. I'm going to give it a good push, see what happens. Oh, just back to the green screen again. Okay, well, I have another Kickstart ROM here. This is a 1.3 ROM sitting here, so let's put this in. See if this works any better. Oh, hey. Oh, yeah, this is looking good. This is normal. You get the white screen while I was trying to look for a disk. I don't have a drive plugged in. Oh, yes, look at that. It's working. All right, so I have a floppy drive here, and here's Amiga test kit boot disk. Let's pop that in. I'll just stick this over here. All right, here we go. Will it work? It's booting. It is booting. Oh, look at that, test kit. Oh, it worked, sweet. And keep in mind, this is all with the Buster chip removed from the motherboard. So that just shows if you have a bad Buster chip, your computer will work. You just won't be able to use your 02 or the coprocessor slot. So if you have a stock 2000 with nothing in it, you don't actually need the Buster chip. Well, I'm not sure if anything else is broken, but it's obviously booting software and the diagnostics are running properly with this chip removed. So just something to think about. The fact that the 2.0 ROM does the green screen, I'm just wondering if it's the chip that's bad. Maybe 2.0 is smarter and can actually detect that I don't have the Buster chip in there. I mean, that's possible, I suppose. I don't know. Okay, so the next logical thing is that this Buster chip is bad. So I'm going to go find another Buster chip in another machine and try it in this motherboard, see if that fixes this problem. And no, it didn't fix it. I tried 2 other Buster chips and the machine behaved in exactly the same way. The CPU halted itself due to a bus conflict. Interesting. All right, well, I guess I need to study the technical manual some more just to look at how this Buster chip works or what it's actually doing to try to see what it's controlling exactly and where the issue may be. Okay, so I've made some progress. You can see here that Kickstart 2.0 ROM is working fine now. That's the original one, the one that I thought was maybe bad, causing the green screen. No, it's actually working. Now, what did I do here exactly? Well, you may notice that Buster is installed in the computer right now, but I also have this clip lead that goes from here, which is actually just picking up 5 volts, and it's going over here to a pin on this LS245. Now, you might be saying, aha, bad trace, right? Because that's typical with battery damage. Not necessarily. I can't actually figure out what's wrong when it comes to traces. But what was I able to do? Buster is inserted in the socket, but one of its pins is lifted and is not in the socket right now. Here's a little snippet from the service manual, and you'll notice there are 2 LS245s, U604 and 603. And they are buffering, or they are transceivers used on the data bus from the CPU to the Zorro slots. The BD0 to 15 goes to the slots, and there are 2 signals that come from Buster, active low DBOE and active low D2P. D2P is the direction control that controls which way these chips are sending the signal, from the slots to the CPU or vice versa. And then the other signal is the enable signal for these LS245s. What I did is I lifted DBOE, so Buster is no longer able to control these chips anymore, and then I just hotwired them using this clip lead here directly to 5 volts, which keeps these 2 chips permanently disabled. It's these 2 right here. In the schematics, you'll see that the enable pin is tied together, so I have it clipped onto one of them, but that's actually disabling both chips. And when I do that, not only does the computer work, but with this hot wire in place, Kickstart 2.0 also works. If I remove the hot wire, then it will do the green screen. Now here's something interesting. Let's look at that pin that I lifted on the oscilloscope. Hopefully I'm not blocking the camera. The computer is currently running. There it is. And if I turn this down, there's full-on activity. So Buster is commanding those chips to turn off and on all the time, which is weird in a way because I don't have any cards installed in these slots, but maybe this is normal behavior. I'm assuming this is normal behavior because I tried different Buster chips and they all do exactly the same thing. And then also, let's take a look at the direction pin, which is the other output that goes to these from Buster. And it's just solid high, 5 volts. It's pulled up to 5 volts, but Buster is connected to that pin. There's continuity, and it's not doing anything. So for sure what's happening is Buster is turning on these 2 transceivers, and they are trying to drive the bus at the same time the CPU is doing that, which immediately creates a bus conflict, and then the CPU just goes into halt mode and disconnects itself from the bus to protect the whole computer so it doesn't keep running and damaging itself. So I have to ask myself 2 questions. Is it normal that Buster is trying to instruct these transceivers to drive the bus like that? If it is normal, then maybe there's something wrong with these 2 transceivers where when they transition between on and off, they cause a bus conflict, a very quick and momentary one. These were both bathed in a lot of battery leakage, so they could possibly be bad. Sometimes that corrosion can make its way inside of chips and cause issues. They don't have any of that blue gunk on them, and I don't think they ever did. But, you know, I don't know what's wrong here. Just for fun, I inserted one of my other Buster chips, and I lifted the same pin. Let's take a look at it. And yeah, we're seeing the same activity on the oscilloscope. And the computer is working with that chip pin lifted. With it in there, definitely same black screen, same halted performance. So it really feels like the fault has got to be either with what's telling Buster to activate those, or it's with these transceivers themselves. Maybe one of these transceivers is bad. I forgot to show you something earlier while I was troubleshooting. So I'm going to probe the direction pin. That's the one that I bent out. It's currently back in the socket, so everything is operating, you know, as it should. And I'm going to turn this on, and I'm going to quickly hit single shot here. Watch this. Okay, what this captured is Buster instructing those to turn on. And then I guess around here, the CPU has enough, and it halts execution entirely, which stops Buster from trying to turn on those transceivers anymore. And we just get these pulses here, and every time it goes low, it turns on the transceivers, and then it stops. So that kind of clued me in that was driving these buffer chips to turn on, and that was causing the bus to go into conflict. So I'm really suspecting that one of these 2 74 LS245s is bad. So what I'm going to do is I'm going to use my cutters here, and I'm going to snip the leg. And if I snip one of them, I'm going to cut half the bus off from causing bus conflicts. So if this is the one that's causing issues, and I cut the enable pin, and I just hold that high using my little clip lead here, then potentially the system will run without a bus conflict. But if that makes no change, I'll put a little blob of solder to reconnect that one, and then I'll snip the other one. And then if that makes no difference, then I think I'm kind of back to thinking that something is wrong with Buster, or not Buster, because I know that chip is good. I've tried different ones, but whatever signals are going into Buster that cause this selection to happen is the issue. Anyways, let me cut one of these. All right, so I've cut the left pin, and I'm going to hold this clip on it, which is going to hold it high, so that chip will stay disabled, but the other one will work. And let's turn on the computer, and nothing. Same thing, we're still getting a bus conflict, even though only half of the bus is going into conflict. So cutting the leg on the right chip was unsuccessful. I just don't have enough clearance there, so it's a little mangled, but it's still connected. So what I've done is I've lifted the leg on Buster, I've connected my little clip lead to it, and I'm going to manually connect it to the left chip, because that's still cut. So that will leave the right chip with no signal at all. It's just going to float. And let's see what happens. Okay, so that's some progress. Buster is connected to the left chip, and it is driving it, is instructing it to turn off and on. And the computer, while we're getting that flashing green screen, it is booting. It's because I have the 2.0 ROM in there. The other chip is not being enabled. So I'm going to remove this right chip entirely, put a socket in there and a new LS245. I'll just fix the pin I cut on this one. I'll resolder that back together. And let's see if that fixes this computer. All right, socket's installed. I put a new old stock from 1991 Gold Star LS245 in here. This is the old one I just took out. The Buster is back in the socket, all pins. Nothing is bent out. So let's see what happens. Oh, look, it's fixed. I can't believe it. Let's boot the test kit here. I'll plug in the keyboard. Okay, so it looks good. Now I want to test out the Zorro slots, because with no transceivers, with the Buster out or these transceivers not working, you're not going to get working Zorro 2 slots. I'm going to stick a memory card into here, and see if the new memory shows up in the test kit here. Here is a Commodore 2 megabyte Zorro 2 RAM card. Hopefully I can get this in. Yes, I can with the power cable like that. There we go. Turn this on, and what will we get? Working 2 extra megabytes of memory in addition to the 1 meg of chip. F1 for memory. And would you look at that? 1 meg chip, 2 megs fast. It's working. All right, next test. Let's take the Amiga 2630 I tried earlier, and let's plug this in. Oh, it's not gonna work with a power cord like this though, will it? Okay, well, let's reposition things a little bit. I'll pop that out. All right, power supply's over on that side. Let's plug this in. I'll plug it into a different Zorro 2 slot just to make sure it's working. And then the accelerator card, 68030, go into the coprocessor slot. Let's power this on. Here we go. It's all precarious. Oh yes, it's working. It's booting. This is awesome. F1 for memory. And there we go, 7 megs of total memory. Fast is 4 megabytes because the accelerator has 4 megs on board, plus I have the 2 meg Zorro 2 in there, and we have 1 meg of chip. Let's run through the memory test here, and I'll allow it to just make sure everything is stable on here. So I went through all the tests in the Amiga test kit. Everything is working great, including the mouse, which I haven't showed working, but I did test it, and it works. And RAM tests are good, and everything is great. This thing is now fully operational. Well, this Amiga 2000 is definitely working. Everything I've thrown at it seems to work perfectly. I'll reassemble it into a case later, put a hard drive, stuff like that in there. But for now, I've booted various things on here, and everything seems to work great. So the last thing to do is to take this LS245 and test it in the old MiniPro here and see if it detects it as bad. I'm always curious to see if it does or not. Okay, we'll just pop that in there, and we'll hit test. Look at that, test error. Failed, total fail. So there is the bad chip. Did it fail because it got battery corrosion all over it? Or did it fail just because it failed? Incidentally, my cutting attempt did end up weakening the leg and it broke off, so I've soldered on a new one, just for testing purposes. But I think everyone knows what time it is. It's time for the old dead part spin, which is looking pretty full. And this chip goes right in. Well, that's going to be it for this video. There is one repaired Amiga 2000 motherboard. I've actually never worked on an Amiga 2000 before, so this was kind of fun to try to figure out how this all worked. I had no idea what the Buster chip did, for instance. Now, I'm going to say one thing. People are going to point out in the comments that there's probably some corrosion underneath the solder mask, and to really fix this board, I have to desolder these components in the affected area, sand the board down, reapply new paint, etc., etc. I'm not going to go through all that for this board, and I think this board is going to work fine for a long time to come. But on the other hand, it might be an experiment to see if this board does degrade and fail over time, and in that case, this may become a donor board for its parts to go on that replica PCB Amiga 2000 I got. That'd be kind of interesting, wouldn't it? Anyway, a huge thank you to Andy for donating this machine to the channel, and that's going to be it. If you liked this video, I'd appreciate a thumbs up. If you didn't, you know what to do. Thumbs down, subscribe for more videos, hit that bell icon if you want to be notified, and put your comments and your suggestions in the comment section below. Thanks very much, stay healthy, stay safe, and I'll see you next time. Goodbye.